So hello everyone. My name is Dangning. I just finished my PhD at Colloque with Federico Galliano. And today, well, you've heard about polycyclic aromatic hydrocarbon PAHs in the previous talks. And today I will take you deep into the aromatic universe with the powerful Bayesian statistics method. So before that, I will present the dust in the interstellar median, and in particular, the very small grains and the polycyclic aromatic hydrocarbon PAHs in the context of nearby galaxies. Then I will present a state-of-the-art observational study of these topics, and with the case study of M82. And finally, I will show you the application in the James Webb era. So I don't have to present all the dust or the important role of dust in the interstellar median. Lara presented with the beautiful interstellar dust life cycle figure, if you remember. But still, for those who are not familiar with dust, I would like to say some words about the important role of dust. For example, dust is important for many chemical reactions, in particular the formation of molecular hydrogen, where you can see the hydrogen atoms form the molecules on the dust grain surface before being released in gas phase. And another important process is the photoelectric effect, where the parts or individual grains under the electromagnetic field radiation, charged particles will be released with the efficiency as a function of the incident photon. And from a macroscopic point of view, you can see the dust can redden. Well, the dust extinction of stellar light is often referred to as interstellar reddening. Given the UV and the infrared observation of a galaxy, you can see the obscured regions that shine in infrared. And also the star formation activities can be traced by HFR, can be also traced by the in the infrared. And that gives the famous Madot plot, where you can see the star formation rate traced by UV in blue is different from that traced by the infrared in red. And if we count both contributions in black, and we can see the discrepancy, this star formation rate can increase by more than a factor of more than an order of magnitude from nowadays to cosmic noon at redshift equals to 2 to 3. A more comprehensive understanding of a galaxy can be shown with the spectral energy distribution. Well, it's hidden, but well, the SED. So that's the energy emitted by an object as a function of the wavelength. Here I show a typical late-type galaxy similar to our Milky Way. And you can see the stellar emission and the presence of gas. And they are mainly absorbed in UV optical and re-emit in the infrared by the dust. And there are also free emission and the synchrotron emission dominate the longer wavelength. And in particular, the near to mid-infrared range contains most solid-state resonance, including the aliphatic, aromatic, hydrocarbon and the silicon bands. To study these features, we need space observatories. And 10 years after the detection of these these bands, called so-called unidentified infrared bands, the first infrared space telescope, IRAS, was launched. And because of the very similar features observed in the laboratory and in the space. For example, on the left panel, we can see the spectra of Otto soot and the Orion bar share the very similar bands at around 6.2 and 7.6 micron. So we suppose that the paths are the carriers of these features. And with more powerful space telescopes, such as ESO and Spectra and Carry, we can study these features in detail, even identify a specific species of these molecules, the furan. And alternatively, we got other proposals of the feature carriers, such as amorphous carbon, as a physically viable alternative to the PAH hypothesis. For the following presentation, I will stick to UIB, these terms, for the spectral features, and the PAH for the feature carriers, since in this presentation, I favor the PAH hypothesis. And this field will definitely be promoted with future generation space telescopes, such as James Webb. Here I show a spectra of an NGC 7469 second nuclear and outflows observed by JBST recently. And you can see the stunning details of these features in this range compared to the first spectra observed by the ground-based telescopes. And at the same time, laboratory study gave us very comprehensive knowledge of these features. In particular, I would like to say that these features are attributed to the vibrational modes of PAHs, such as the carbon hydrogen bond exchanging mode, which emit at 3.3 micron, and all the CH out of plane banding motion, which emit at 11.3 and 12.7 micron. Remember this wavelength, that's the basis of the analysis that I will present. And there are also other properties of these molecules and grains, such as the structure, the charge state, and compactness, and and the size distribution, of course. And to study these UIBs, the mid-infrared feature, we need to cover the full range from around 2.5 to up to 30 micron. And to do that, we considering the comparable resolution and the sensitivity, we can combine a Carry IRC spectra and the Spectra IRS, or alternatively, GWST, near spec, and MIRI spectra. For example, these are the Carry spectra. In red, it's a Centaurus A, is extracted from the Centaurus A, which is an early type galaxy with a dusty lane across the center, and so that you can see the strong silicate feature absorption with all these emission features And similar to our Milky Way, NGC 1097 is a late type spiral with a weak AGN already. Okay, so and also the blue compact the Dove galaxy, where these features are weaker, with strong emission lines. Well, I should be quick. So these complex data addresses the following questions, including the variation of band intensity in terms of as a function of the environment, and eventually linked to the physical condition. And well, that's a lot. So I will be quick for the data processing step. In order to combine all these data from different instrument modules, I extracted all these spectral cubes, for which I present the footprints here. And finally, the green Akari slits are combined along with the Spitzer data. And after processing the Akari and the Spitzer data from the pipelines, official pipelines, I homogenize these data and do the calibration, and eventually propagate the uncertainties with my workflow. And to recall a little bit this morning session about the uncertainties, I take into account the pipeline, that is the systematic uncertainty, the pointing uncertainty, for which I converted to the flux uncertainty, and the calibration uncertainty. And I propagate all these with a Monte Carlo bootstrapping method. And finally, we got these beautiful spectra for one of the spectral cube. And to decompose them, I apply the physical model, including the stellar and the dust continuum with the parameters in the parentheses, and the emission lines with Gaussian profile, because it's not resolved. And most importantly, the UIB features modeled with split Lorentzian method, accounting for the unharmonicity of these emission features. And linearly combine all those features, I apply the foreground extinction, and that's the total model I have. With this model, I eventually use the statistical sampling using the Bayesian method. Well, the normal, standard Bayesian method applies the you can imply the posterior distribution of each parameters given the data, and I use a Gibbs sampling to sample these distributions. And the originality of these of my code is the application of a hierarchical model on top of the Bayesian method, for which I applied I applied the hyperparameters on top of the model parameters, and at the end we can sample the posterior of all the parameters of all the observations to a global distribution. And to test this model, I did a simulation with my model, applying different signal to noise ratio and feature to continuum level, and I fitted them with different method, including the least square, non-hierarchical Bayesian, and the hierarchical Bayesian method. And well, I should say here, I wanted to suggest that it's not efficient to apply the model calculated from each representative parameter, such as the mean or median. Instead, we calculate the median model. That is the model. calculated from each step of the MCMC. And that's the results for non-hierarchical and hierarchical method, where you can see the hierarchical method has smaller uncertainty, final uncertainty compared to the Bayesian one, normal Bayesian one. And I will pass all these analysis of parameters because it's very complicated. But here I just want to show that in my model, it's the parameters distribution are very complicated, for which they can have a multimodal profile, or with a low signal to noise ratio, you can't efficiently sample these parameters. And I did some effort to accelerate this method, which is very time consuming, but eventually it's very practical for a normal run. That's more than 3 days, but still. And finally, I wish I still have some time to present the results of the scientific results of using my model. So by linking the band ratio variation to different physical conditions, we can eventually using these band variations to trace different physical conditions in the interstellar medium. And taking MED2 as an example, I first decouple the effect of a size distribution and the charge ionization effect with calculated grids here with the different size distribution and ionization fractions. And that's the model we used. And that's an alternative method to calculate the grids. And we can see in the center the size of a pulse increase from the center galaxy to the outflows. Another application is the hydrogenation effect and the radiation field. Okay, I will finish soon. Sorry. Okay, very soon. Where you can also apply this method to study the physical conditions in different regions, because we got the specially resolved observations. And I don't have time to explain all these in detail, but what I can say is that our method is very pertinent to GWST data. And with the high sensitivity of GWST, we can study the small band variations, which cannot do with cannot be done with Spitzer, even the Spitzer, and also the spectral resolution can help us with different more features. And I will leave this takeaway message if you got questions. Thank you for your attention.